Ciao, Cradero Cradole here to welcome you to the first in a series of 5 on motion physics, acceleration due to gravity.
Things will accelerate by speeding up if they're dropped from a high place. Galileo found that he could not measure motions of falling bodies directly because they accelerated too quickly. Instead, he did experiments by rolling balls down inclined planes so that the acceleration was much slower. Then it was Sir Isaac Newton who first postulated gravity as we know it, a force exerted by anything with mass on anything else with mass, according to the product of the masses used and inversely according to the square of the distance between them. So after much testing with pendulums, he refined acceleration due to gravity as 9.8 meters per second squared. That meant that all objects would fall to the earth 9.8 meters per second faster each second that they fell. Each year, I demonstrate this concept by dropping 2 11-meter strings off the tallest part of our school. One string has evenly spaced washers and the other has washers separated exponentially further apart towards the top of the string. They hypothesize the rhythms that the washers will generate by the sound of clinking washers hitting the ground when the strings are dropped. We find that the one with linear spaced washers makes an exponential sound because the washers that fell further through the air at the top sped up more, so they caught up with the others at the bottom of the drop. And the string that had the exponentially spaced washers made a linear rhythm since they were spaced according to how much they would eventually speed up during their time aloft. Now obviously it's not a perfect world, so this nice clean sounding acceleration of 9.8 meters per second squared doesn't work. If we were to drop our strings from really high places like out of a plane, it turns out that air molecules will create enough resistance to slow the speed of acceleration all the way down to zero. That doesn't mean that you stop in midair, it just means that you stop accelerating when your weight equals the fluid friction of the air, or air resistance. Then you've reached what is called terminal velocity. For a human, it's close to 120 miles per hour, or 200 kilometers per hour, depending on how much surface area you create, spreading limbs or holding them in. So if we exclude air resistance, we can work out some simple calculations for how fast something should be falling at a given amount of time during a fall. For example, if something fell for 6 seconds, it should be falling 9.8 times 6, which equals 58.8 meters per second. Isaac Newton performed many different experiments with colliding different masses. He realized that the force of colliding objects was different when he changed the acceleration, like it did when changing the masses. So the force of an object causing a crash was as much affected by the acceleration as it was by the mass. Also, with pendulum experiments at the equator of the Earth, the pendulum string length would have to be shortened by a tiny bit for the period to equal that of a location closer to the pole, meaning that where the equator bulges, less gravity pulls an object. Acceleration due to gravity is caused by how much mass the Earth has, and other planets don't have exactly the same amount of mass. The acceleration due to gravity on the Moon is 1/6 of the Earth, so you would weigh 1/6 of your Earth weight on the Moon. Also, you could theoretically weigh anything, like 0, if you weren't being accelerated by gravity, like somewhere between the Earth and the Moon, or a lot more if you were close to something really big, like Jupiter, the Sun, or even something with crazy mass like a black hole. Another widely known of Newton's realizations is that all objects of any mass, if dropped at the same time, would accelerate the same amount and would therefore hit at the same time on the Earth's surface. Again, this was proven using pendulums and different masses on the bob. But why doesn't something with a much larger mass accelerate more when dropped? It weighs more, so there's more force pulling on it. It's because the more mass something has, the more inertia it has, or resistance to change. So it takes longer to get going once you've dropped it. This means each time you increase the mass, the slower it is to respond and get going, thus canceling out whatever increased gravitational effects that it might exhibit.